So, so last class we started working with matrix models. Okay, so we had thought a bit about how to do operations with matrices, matrix multiplications, and now we are going to use that in order to study something that there's really no, I call this I have this tutorial that I call large systems of ODEs, right? But then it's just to show you how to work with systems that have a certain structure to them, where you can have many species, okay? Many equations, many populations or subpopulations, okay? So, and usually in order to do that, we have to be able to express the system of equations in a very compact way, usually using matrices, okay? So, so yesterday we talked a bit about, it's funny that when you, I don't know about you, but when I was in, I don't know, high school, matrices were a bit like, well, kind of boring, right? Because you have to do these multiplications and so on, right? Kind of boring. But then when you learn more math, right? So the interesting thing is that, well, if I can reduce a problem to a matrix, then it's always easy to solve, right? So so really matrices are really good, right? Because they are always easy. Problems that you can reduce to matrix problems are always easy and efficient to solve. So so this is a good news, right? So I am not sure if it is, there's no general theory here, like general, but I want to explore a few examples where we are going to see systems that can have many equations, okay, and see how we can think about them and how we can implement them into the computer, how we can look at them, okay. So I think I go to the examples themselves, okay. So the first one that I want to show is the generalized Lotte-Volterra equations, okay. So this is, I think I'm going to write down this in the board, okay. Yeah, I think it's better than just scrolling through the text. Okay, I'm going to tell more or less what is in the text, but then I think it's much easier to understand if I use the board, right? Yeah. Okay. So what is a generalized Lotte-Volterra, right? So yeah. The idea is that the idea of this is that you have seen predator-prey Lotte-Volterra equations and competition Lotte-Volterra equations, right? And in all of them, what do you have? You have something like, for instance, the competition equation was like this, right? So it was like this. You had R1 and 1, and then here you have, I think Roberto wrote it in a different way, right? And I also wrote it in a different way. But if you just change the constants, okay, you can write this as R1 and 1 times 1 minus intraspecific competition, that I will write like this, intraspecific competition, and interspecific competition, okay? It is like this, yeah. Right, so coefficients representing competition between with N1 with N1 and N1 with N2, right? So you can, so these are exactly the same equations that you have seen before, okay? Just written in a slightly different way. Instead of putting a carrying capacity here, I just, the other form was like this, right? It was K minus K1 minus N1 minus alpha N2, right? Divided by K. Yeah, this was the form that you had before, right? Yeah? For this term here. But then K1 over K1 is 1, and 1 over K1 is C11. So C11 is the inverse of the carrying capacity of the N1 population. And then alpha divided by K1 is C12. Yeah? So it's pretty much the same. I just changed the way I call the constants, right? Yeah? Okay? Clear? Okay. And then we can do this also for the second species, right? So I have now C22N2 minus C21 N1. Okay, so again, C22 is the interspecific competition, right? So it's the effect of competition of population 2 on the population 2 itself. Okay, and C21 is the effect of the population of species 1 on species 2. Okay, yeah, so it's always like this. Okay, and then the nice thing about this is that it's easy to generalize. Okay, you can just come here and say, okay, you can go here and you can say, well, if I have more species over here, what if I want to introduce a third species, right? How do I introduce a third species? I add another equation here, N3 dt. I have an R3 N3, and now I'll have 1 minus competition of this species with itself, and then with the other species, with the effect of 1 on 3, and the effect of 2 on 3, okay? Yeah? And then I have to add the effect of species 3 on the other 2. So I have new terms here that are going to be now minus C2, 3 and 3, and minus C1, 3 and 3. Yeah? Easy, right? Easy. So, and then you can keep doing that, right? Moreover, right, there's still something else that you can do here, right? So, when I do this, if all the coefficients are positive, okay, this is competition, right? Because increasing species 2, I decrease the growth rate of species 1. Okay, so all of this is competition. But you could also say, okay, maybe there's not only competition in this world, right? There's also consumer resource interactions. There's also what? There's also positive interactions, right? So what are positive interactions? It also includes mutualism here, right? So what is the difference then? Is that the signs are different, right? So if, for instance, if species 3 predates species 2, right? So it gains from when it increases species 2, right? So it would have that when I increase species 2, I increase species 3. So then this sign here instead of being a minus would be a plus. Okay, so this means species 3 gains from species 2. Species 2 keeps decreasing when I increase species 3 because it is now predated by species 3. Yeah, so I can have competition that is minus minus. I can have predation that is minus plus, and I can have also plus plus. Okay, that is mutualism. Okay, I include terms here that are positive for both, right? So, for instance, if I change the sign of C21 and the sign of C12, I put both of these with a positive sign, right? It means that they cooperate. I increase species 1, I help species 2, right? I increase the population of species 2. I increase species 2, I increase the population, the growth rate of species 1 as well, right? So I can have all of them. Yes?
It's just a little fast for me. Can you?
The last part, or what is it?
Yeah, the last part.
The science part. Okay. So if I wanted to write a model with mutualism between these two species, right? I would just replace, because you see this part here is the growth rate, okay? And this is R times this is the per capita growth rate, okay? If C12 is positive, there's this a minus here, it means that as I increase N2, as I increase the population of species 2, I decrease the growth rate, okay? If the interaction between these two species, they are mutualists instead of competitors, right? What should I expect instead? I should expect that when I increase one, the growth rate of the other increases, right? So the sign here should not be negative, it should be positive. Okay, so if this sign is positive, then when I increase N2, I increase the growth rate of species 1, right? This means N2 has a positive effect on N1, right? And since this is mutualism, this should happen also in the other direction, right? So when I look at the equation for N2, this is the growth rate of species 2, right? And now I'm saying, okay, if the effect of N1 on species 2 is also positive, right? When I increase N1, I should have the growth rate increase as well. So the sign of this term here should not be negative, should be positive. Yeah? Clear? Okay. Okay, so what I'm telling you now is, okay, then all of these terms would have either sign, okay? It would be either positive or negative. And yeah, I just want to caution you a bit about positive terms, because it's possible that in this kind of model, if you put a lot of positive terms, a lot of mutualisms, it's possible that the populations will help each other out so much that they will they will increase it to infinity. Okay, yeah, that may happen if you're not careful with the parameters. Okay, so this is not the best model for mutualism because it has this kind of risk, okay, of possibility, right? So you, okay, so if you wanted a model specifically targeted for mutualism, it would include more terms. But here, what I want is to study a more general model that includes both competition and mutualism and predation prey. Okay. Good. So this is the generalized loss of Volterra, and now I want to do this for any number of equations, right? So what do I do, right? So if instead of having only 3 equations, right, 3 equations, we can still write it on the board. It's more or less easy to include in the programs, right? Yeah, you have written programs with even more than 3 equations. Not so bad, right? Yeah, it's not so complicated to include this in your program, right? But what if I told you that I could try to look at a network of interactions between species that has, hundreds of species. Huh? How do you do that? Right? So there are, trophic networks, right? Yeah? Trophic networks, or maybe pollinator networks. You have a lot of networks, right? So you have networks of interactions and so on, right? So these usually have many species, right? Yeah? So I don't want to code by hand hundreds of equations, do I? I hope not, right? Yeah? No, not at all, right? So what do we do, right? So what do we do? Well, the process here is that we have to write these equations in a more compact way, right? So then we have to notice the structure, right? So if I have more equations here, suppose that I have n equations, right? With n species, right? Well, if I have n species, I'll have n equations, of course. Right, and now let's see what it look like for this equation here with n species over here, right? So you have to have n terms here, right? It's one for n2, n1, n2, n3, n4, and so on until n, small n. Okay. I think because I'm using n, I'll just do as I did that and switch to x. Is it okay? Just switch to x as a notation. Yeah. So I'll write the equation for x1, dx1 dt, okay? And this is going to be R1 x1 multiplied by 1 minus what? Now this minus here, there will be a summation of terms, okay? So I will always have C1, and the second index is going to be the index of the species that I'm looking at that is competing with species 1 or predating species 1 or collaborating species 1, okay? So we have C1 and some J, right? So C1J, okay? So this is the sum of C1J Xj, okay? Right? With J going from 1 to n, that is the sum of over all of the n species, okay? N populations. Okay or not okay? Yeah? And of course, if I did this for species 1, what is going to be for species 2, right? Species 2, I don't even need to write it again, right? So species 2, the dx2 is going to be R2, X2, 1 minus C2J, Xj, yeah? So I just change these indexes here. And of course, then I can write this for any species I, okay? So gxi gt is ri xi 1 minus cij j, okay? Good? Yeah. There. Oh. Não dá pra fazer.
I don't know if I understand it correctly, but isn't it going to be a problem if different species have different signs? Like one's negative because competition and the other one's positive
Well,
because mutualism?
all the populations are going to be positive, right? Yeah, because populations, right? They are the populations themselves are always positive, right? There's no meaning to negative
the
populations.
effect
But
of
then the
one
interactions among them can have either sign. So I have to, if I want to know the interaction between species I and J, I have two parts of that, right? So the effect of J on I, and then in the equation for J, I'll have the effect of I on J, right? So if both of them have positive signs, then this is a mutualism. If both of them have negative signs, this is competition. If one of them is positive and the other negative, one predates the other. Right? So this is the sign is determined or are determined by the kind of interaction. Yeah? And any signs, any combination of signs is possible. Yeah? I'm not so sure I understood the question.
Yeah, because you're summating the effect of different species,
Yeah.
right? Like a lot of populations.
Yeah.
But if inside this summation, one is negative and the other one's positive, we don't have a problem with
Yeah,
that?
there's no problem, right? So for instance, let's look at this one here, for instance, right? This means if this is a plus over here, right? This means that, okay, entry is suffering, so this growth rate is decreasing because it's competing with itself, is decreasing because it's competing with species 1, but there's a positive term here because it is predating species 2, right? So it gains from consuming species 2 and loses from competing with species 1 and 3. Yeah, so and then it all comes together when you sum them, right? So there is a kind of a strong assumption here that only the pairwise interactions are modeled, right? So you don't have interaction between 3, right? So for instance, this is possible in nature, of course, right? So if you have a lot of, this is very common, especially in trophic chains, right? So if you have a top predator, right? If there are a lot of top predators, then the intermediate predator, the intermediate consumer, perhaps in order to avoid being predated, it also stops hunting, and then it decreases the attack rate on the basal resource, right? So this is almost, but this is an interaction that involves 3 species, right? So it's like, it would be like, well, species N2 stop and 3 stop predating species 2, so this coefficient is going to be reduced due to the presence of the other, right? So this is not considered here, okay? I only have pairwise interactions, and I'm assuming that all of them are independent of the other species, okay? It doesn't matter, so this kind of thing is not that counted for here, okay? Yeah?
I understood now. And lastly, you put a minus sign there and
yeah, maybe I should put a plus here, right? I don't know how I did in the notebook.
yeah, you put a plus here in
I
the
put a
tutorial.
plus, yeah. I think it's easier to put a plus because then it's easier to interpret, right? So I put a plus over here. And what I do here is essentially that I'm saying that competition means that these are negative, mutualism means that these are positive, and a positive and a negative means predation, right? Yeah, just, yeah, because I was using negative here because I started with competition, right? And then, yeah. But of course, I can just say that this is all my plus, and I have minus here, okay, yeah? Or this C11, C12, C13 are going to be negative, okay, because this is competition, right? Yeah? Just because I started with a model that already assumes that all of them are negative, yeah? Okay, more questions? comments? Is it clearer now? Yeah? Okay, so I have this formulation here, okay? And now, of course, this already helps a bit because now I don't have, I can always write down this expression, right? But it's still. So this is already, I can more or less think how to do this, right? So to make a sum, I can either use an array summation or maybe a for loop over here. And if I have I equations, I would maybe also write this in a loop, right? Yeah? I loop with I from 1 to n, I can write down this with loops. But then you can be even a bit smarter than that, right? Because I can also recognize that this thing here is essentially a matrix product. Yeah? You remember that I wrote this in the last class, an expression that is just like this. What is this here? I will define a matrix that is the competition matrix, or I use it A over. Let me use A over here also. Yeah. Because this is, what would be C? I will C, okay. C. And then C is going to be C11, C12, C13, and so on, up to C1n. And C21, C22, and so on, C2n. Of course, this has n lines over here, right? And then this ends with the nth line, right? So Cn1, Cn2, and so on until the Cn over here, yeah? So, and this thing that shows up here is just the C multiplied by the vector x, okay? So this is, so let's do this example here, for instance. Okay, let's do with 3 equations only. So I have C11, C12, C13, C21, C22, C23, C31, C32, C33, okay, multiplied by the x vector that is x1, x2, x3, okay? So this is x1, x2, x3. And then what do I have here? I have C11, x1. This product here, right, is going to be C11, x1 plus C12, x2 plus C13, x3, right? And the same for the others, okay? Yeah, C21, x1, C22, x2, C23, x3, and so on, right? C21, x1, oops, there's a plus here. C32, x2, C33, x3, okay? And you see that the first part here is this sum in the equation for species 1. This part here is what appears in the equation for species 2. And this one here is what happens with species 3, right? So I can, with this, I can write this equation here in a vector form, okay? In a vector form. So I have here, I have to multiply. So if I want to write now dx dt, so dx dt, right? Oops, dx dt. Okay, what is this? Is a vector that is gx1 dt, gx2 dt, and so on until gxn dt, right? So I have a vector like this. It has to have in each line this, what is in the right hand side here, okay? So I have to have, for each line, I have to have I times xi times 1 plus this matrix product here, okay? So this part here I have to take, now instead of having a list of parameters Ri, it's better to just have a vector of airs, okay? So I say that I have a vector here, and I want to do a multiplication element-wise with x, okay? So there's a symbol for that. This is not very common in mathematics, but it's common. There's a symbol for that. That is a funny dot, right? So it's a dot with a circle, okay? What this means is exactly this. I'm going to multiply term by term. So this is going to be air, the vector of airs, multiplication. Oof. I'm not very used to draw this, yeah. Term by term with x, what is this, right? So if I have if I have a so if I have a vector R that is R1, R2, R3, right? Then R, this product here, R times X, is going to be what? Is going to be R1, X1, R2, X2, R3, X3, right? So it's a product of two vectors that is element by element, right? So it's just what happens when you multiply two arrays in the computer, okay? It does it element by element, okay? So this is it here. And then I also have to multiply it by the result of summing this vector here with 1, and then multiply it element by element as well, right? So I have to take this and this product here with 1 plus C multiplied by X, okay? And this is the equation that we want right over here. You see? So if I want to calculate the right-hand side of this set of equations, I have to take the vectors of R, multiply by the vectors of X, multiply by 1 plus this matrix here, multiplied by X, okay? And this matrix here, this has a name in ecology, okay? This C here is usually called the community matrix, okay? The community matrix. I think you're probably going to hear more about this next month. Community matrix, okay? The community matrix, and or maybe Paula is going to talk a little bit about it, or maybe she has already talked about this. I'm not so sure. No? Okay. The community matrix, right? So the community matrix tells you which interactions have which strength with each sign, okay? So if I have a system, a logical community with many species, I can know the interactions between them by trying to measure the community matrix, okay? So this is one way of studying it, okay? Of course, things are always a lot more complicated in practice because this assumes that there are no higher order interactions, so a third species doesn't change the interaction between this pair, okay? And also I'm kind of assuming that everything is linear here, right? So you have always functional forms type 1, right? So I don't have saturation, I don't have, functional form type 2, and so on, right? So this is simplifying things quite a bit, but then when you want to study hundreds of species, it's hard to keep track of all of that for hundreds of species, right? So it's a lot more parameters, okay? So far, so good, yeah? So with this formulation now, so you see, I took something that looked very complicated, like, I don't know, 100 equations, and now I have a single equation written out in a matrix form, yeah? And then these now, right, you see, there are actually only 2 parameters, okay? In a sense, right? So I have the vector of growth rates and a matrix that is the community matrix. And this is all that I need to pass to our function in order to be able to calculate all of this, okay? I don't need to have thousands of parameters, okay? Well, there are actually thousands of parameters, right? So if I have a community with 100 species, this community matrix is 100 by 100. That is 10,000 elements in the matrix, right? Yeah, so I actually do have 100 values of growth rates and 10,000 values of interactions, okay? So yeah, there are a lot of parameters, but they can be represented in a very, very compact way in this matrix over here, yeah? And of course, in a real community, a lot of species don't interact much, right? So they would usually be 0, not some value that you need, right? So many of them don't interact at all, and then you just put zeros, and that's okay, yeah? So they're not like there were 10,000 parameters to measure, right? Questions, people? Okay, everyone with me? So let's try to simulate this. Yeah? Okay, so let's do now this in the computer. Okay, so let me switch here. So these are the exactly the equations that I just showed you, and they look like this. Let's go down here. Maybe, is it better if I, probably, right? If I turn off this light. Or is it better to not turn off the light in order to see the board? Is it okay? Yeah, it's fine. Okay, so, well, the equations are here in the notebook as well, right? So, okay. So here we are. So we have this notation here. I wrote this with A instead of C, right? So it doesn't matter. So we have this. Yeah, here I did something that is mathematically incorrect, but it's usual, right? So I wrote, this is a vector, I summed this with a number, right? So technically this should be also a vector in order to sum, right? But then, yeah, you got it, right? So I have to sum 1 to every value of every vector over here. 1 plus this, 1 plus this, 1 plus this. Yeah, so this should be a vector of ones, okay? But then when you use NumPy, if I just sum a number with a vector, this means sum a number to each element of the vector, yeah? Good. So, so here we are, and now let's try to implement this in NumPy, okay? So I import all the things here, and now this is our generalized logic Voltaire. You see that it receives x and t, as always, and then a vector of errors, right? So our parameters here, they don't have to be numbers, okay? They can be arrays, okay? I can pass arrays to my function, okay? This works. And then I have an array, a single array here, a one-dimensional array of growth rates, and a two-dimensional array that is the community matrix that I told A instead of C here, yeah? And now this returns what? So R times X, so this product here is the element by element product. This one as well. I have 1 plus, and now if I want to do matrix product, I have to use dot instead of the asterisk, okay? I think we discussed this already last class, right? Yeah, the dot product, okay? And that's it, right? When I do this, I get, as a result, a vector with the right-hand sides of all of the equations, yeah? I think that is really, and so you see all this complicated thing here, and there's only a single line of code inside here, yeah? Isn't that amazing? Yes or no? Yeah? So it's so complicated, but then my generalized logic Voltaire function here is a single line of code, yeah? It's nice, right? It's very, very powerful, yeah? So, and one nice thing about this also is that I didn't specify in this equation here what is the number of equations. You see? I could use this ode to treat a system with 3 equations, with 3 species, or with 10, or with hundreds. So it's exactly the same code, right? But then you have to be careful, right? Because if it is 100 species, then the vector x that is going to be passed here, what? Nosy. Yeah, over. The x here, so the initial condition that you pass has to be an array with 100 elements, R has to be an array with 100 elements, and A has to be a matrix 100 by 100, right? So if I try to mix this stuff here, then things won't work, of course, yeah? So I have to create these arrays in the correct shapes, okay? Okay, so now let's try to invent, I definitely don't have examples of, of 100 elements here, but then let's try to invent some stuff here, okay? So now let's start with only 5 equations, okay? Just to be modest, yeah? Okay, only 5 equations. This, you remember NP point dot ones and dot zeros, right? So this creates an array with ones, and this is an array with 5 ones, okay? So let me maybe print R over here. I'll print down there, okay? And now zeros returns a matrix n by n, an array n by n here, only filled with zeros, okay? Okay, now what I told you before, right? So the diagonal elements, the values, the carrying capacities, the interspecific competition terms are the diagonal, right? So C11, C22, C33. What are these values here? They are interspecific competition. They should always be negative, right? Yeah? They should always be negative. So I take this matrix filled with zeros, right? And there's this function that is very convenient that is called fill diagonal, right? So I take the matrix A and I set all of his main diagonal with -1, okay? If you want to see more details, I recommend you to type help fill diagonal to see exactly how it works, okay? And now just to, before doing that, right, so let me run this and see what comes out, okay? Let me print R and A here, okay? So, yeah. Running for the first time, okay? Yeah. So let me print R and A over here, okay? So R has shape 5, I think one-dimensional, with only ones, right? And A is 5 by 5 with -1 in the diagonals, okay? Maybe I should print this separately just so it is, yeah, it's all right here. So it's easier to see, right? So yeah, now it's easier to see that the main diagonal is -1 and all the rest is 0, okay? But then this is kind of boring, right? Because in these equations here, there are no interactions between the different species, yeah? I only have, each of them are independent. There are no interactions. All the interactions are 0, you see? Yeah? So what I'm going to do is I'm going to introduce some random parameters here, right? So I have this function here called NP. This is inside NumPy, right? So NumPy there's this random submodule. It's a submodule called random, right? So and inside it you have functions that generate random numbers, okay? So this is, I think you have probably used it in R, you have used R norm, right? Yeah? R norm. So this is exactly the same as R norm. I think the order of the parameters are a bit different, right? But then there's a log that is the mean of the ocean, scale that is, I think that is the standard deviation, and size is that number of values that I want as an output, right? So I can do this, a single number returns an array of this size. If I put two numbers here like this, I have pretty much like this here, right? So I have a matrix n by n, right? So I have 5 by 5 random numbers, okay? So here I have a normal distribution here with 0.1 standard deviation, and I sum this to R, right? Remember, plus equal. So this means that R now is the same as it was before, plus these random numbers here, okay? And A, the same thing, right? So A is the same as before, but now I'm adding these random numbers here, right? So when I run this again, now R, you see, it's close to 1, but it's slightly different than 1, okay? Because I put a small standard deviation here. And the same goes for A, right? So you see that the main diagonal is still close to -1, okay? So they kind of dominates, but then I have all kinds of different values over here, yeah? Nice? So it means that all species, all 5 species are interacting with all the others, right? So for instance, I have here that A21 here, right? So the effect of species 1 on species 2 is negative. And the effect of species 2 on species 1, that is this term here, is positive, right? So it means that in this case, I have a kind of predation relationship, okay? Species 1 increases, it's benefited by species 2. Species 2 has a detrimental effect for species 2, okay? Species 1 has a detrimental effect for species 2, yeah? Right, and some other cases here, for instance, let's look here. So species 1 with species 3, right? So both of them are positive, okay? So this means that species 1 and species 3 has a mutualist interaction, okay? Yeah, so this is, there's no real ecology here, just showing random numbers, okay? So, yeah, but just to illustrate, okay? And now I want to solve the system, okay? I want to solve the system. What do I have to do? I have to set the times and some initial conditions. I'm going to start with everyone equals to 1, okay? So, and then I just ordained with my GLV function here, my initial condition, time, and the 2 parameters. You see the 2 parameters are only R and A, for their vectors. Nowadays, they are arrays, right? When I do this, it runs pretty quickly, and now I can plot this here. I see this plot here, right? So you see that all of them survived, yeah? All of them survived. You see that this is still 0 weight here, okay? So all of them, so some species are a bit better than the others, but yeah, okay? I would even have included a legend, but I'm not going to because later on it's going to be a mess, right? So, yeah, okay. Questions, comments? So let's do something interesting here, right? Because this model here, this has been the topic of a lot of debate in ecology since the 70s, right? Because one thing that Robert May has done in the 70s is that there's a very controversial thing here, is that he said, okay, the larger the system, the larger the community, the less stable it is. And how did he come to this conclusion, right? He came to this conclusion by just taking these equations and looking for what happens when I have larger number of species, okay? So I will stop printing A over here. Well, I don't even need to print this again, but anyway, let's just print just to check that R and A are the shapes that we want, right? So they are shaped 20 and 20 by 20, okay? So yeah, just to check if the shapes are correct, okay? Okay, and now I integrate this again, and then I run this. It is and now you see that some species are going to extinction, okay? So, so one thing that May proposed is that larger systems are less stable than, or less stable than smaller systems, and this runs contrary to at the time, the current thing at the time, right? So the common thinking that larger systems, more complex systems, were expected to be more resilient, to be more stable, to be more functional, right? And this, at least this model doesn't correspond to that idea, right? Of course, there are a lot of discussion about this. I am not going to go into this right here, but it's interesting that even a system that has, and he also did this with random coefficients, okay? And this is perhaps the crux of the debate, right? Is it okay to just throw around random parameters and say that this somehow is related to nature? Yeah. So it's, or maybe in nature you don't really have random parameters. All species are subject to evolutionary pressures. We expect parameters to be actually very special in a sense, because they are the result of a long-term process of evolution and so on, right? So maybe this is not true at all, right? Yeah.
Just for curiosity, I ran the code for 20 species, and neither of them went to extinction.
Yeah. Well, this is because we try to do random things here, right? So every time you run this, you're going to have a little bit different parameters, and sometimes they won't go extinct, okay? So I kind of was unlucky here, right? Maybe if okay, here and none of them went to 0, right? This is small, but not 0, yeah? So now I was as lucky as Gabriel, right? Gabriel? Yes, okay, as lucky as Gabriel, right? But then what if I went further, right? So I want now to go from 20 to 100 species. I always do this. Now with 100 species, this is a mess, right? So maybe this is why I had this here. So maybe if I plot in a large scale, I will see if there are species going to extinction, right? And there are a lot of species going to extinction, okay? And actually, is not that you always have extinction, but as you increase the number of species, the probability of some of them going to extinction increases very quickly, right? So so this is because this is random, right? Of course, there's some chance of there's none of them going to extinction, okay? But then as you increase the number of species, this becomes ever less likely, okay? Yeah? Yes.
I just would like to understand what exactly are the numbers on the y-axis. I know it's the result of the equation, but
They are the populations, right? So this is, I have here a system of now 100 equations, and I have then dx1 dt, dx2 dt, dx3 dt, 2dx100 dt. That is the population of species 1, population of species 2, population of species 3, up to population species 100. And then I'm plotting over time the population of each of the species, okay? But now I just changed the scale here to be a log scale. So that's very small numbers. I can see that they're going to 0 here, okay?
yes,
So-
yes. In this case, it's log number, but before, on the other one, was it literal value of the
Before the log
populations
scale.
or what?
Before the log scale? What do you mean?
This
Here.
number in the y-axis, are those literal numbers like populations of like 5 individuals, or is it something?
Oh well,
something
I
else?
put I put the diagonal of to -1, right? So if there were no interactions at all of the species, all the populations would have a carrying capacity of 1, right? So of course this is not individuals, right? Because you cannot have a carrying capacity of 1 individual, of course, yeah. But then this is kind of arbitrary units of populations, yeah.
When you sum the R norm to the matrix,
Yeah.
you remove this -1 from everyone.
I don't remove them
No,
exactly, but I
yeah,
change
you
them.
change it.
I change them. Yeah, I change them. Yeah, they are still going to be close to -1 because now they're going to be -0.9, -1.1. Yeah, but since I'm summing a normal distribution that has 0.1 standard deviation, it's very, very unlikely that this comes close to 0, right? So yeah. It's very, very is an understatement. It's like astronomically unlikely, right? So yeah, because this would be like 100 standard deviations, right? So this is yeah, pretty much impossible. You try to run this millions of times and wouldn't find it even once. Yeah. More questions? More comments? So I'm not really. There's a long discussion about this generalized loss of Voltaire, about this complexity stability relationship, but a lot of things that were this discussion that started in the 70s, it started from this set of equations. Yeah. So it's kind of interesting. Yeah. So I don't buy many of those arguments. Okay. But then this is a question for more complicated discussion. Okay. Okay, so let's go now to our second example, okay? Let's go to our second example. So this is going to be patch model, okay? So maybe I go to the board again. Yeah, so I think it's better to explain. So, oops. No, this one. Okay. So, the example that I want to talk to you about now is what we call patch models. what are patch models, right? The idea is that I have a region in space, right? So we have, for instance, a landscape or something like this, right? So we have a geographic area, okay? Right, so this is a view, a satellite view, for instance, right? And we have regions in space that, from the point of view of some particular species, they are separated, okay? Maybe I have a large region, I don't know, a forest here. I have some small patches of forest, maybe another large one here, okay? And they're separated by regions that are not, so these here are let me say it like this, right? So these regions over here, they are habitat. And these regions in the middle here are non-habitat, okay? Of course, when I tell this, okay, of course, I can think that I think the easiest example is thinking of forest and fields, okay? Forest and fields. But of course, this definition here is strongly species specific, okay? So some species are going to look at this and say, oh, but I don't like forests, I like fields, okay? Yeah, of course, right? Some species will look at this and say, okay, this is all the same to me. I can go over all this region, it's all the same. And of course, some species will look at this region and say, okay, I only like forests. I can only reproduce, I can only live in forests, okay? But even those species, so I'm drawing this from the point of view of a particular species, yeah, that sees the landscape in this way, okay? I'm not saying that all species, all the community sees the landscape in the same way, okay? But from the point of view of some species, I can divide this region in this way, and what I mean by this, right? I mean that in this region of habitat, I expect the population to be able to grow, to reproduce, and so on. I expect it to not be able to live in the non-habitat. But then, it doesn't live in the non-habitat. And finally, this in the landscape ecology is usually called the matrix. Yeah, the matrix is the region that is the non-habitat region, okay? But I tell you here non-habitat because we're talking so much about mathematical matrices, okay, that I don't want to confuse stuff, okay? And so, of course, it doesn't live here, it cannot live here, cannot grow here, but it is able to cross, right? It can migrate from this region here to this region here, maybe from this to that, from this to that, and so on, right? So it can cross the non-habitat regions. It can migrate, okay, across different regions, okay? So these regions of habitat here, we usually call this patches, okay? This is a patch, right? So I have a patch of habitat here, another patch here, another patch here, another patch there, and so on, okay? So these are patches, okay? Yeah? So far, so good? Yeah, this is simple question.
Is it possible to derive a relation between carrying capacity and the area of the patch or something like that?
Yeah, you can think about it. Yeah, sure. Certainly. Yeah, I thought about this in a moment, okay? More questions? Okay, so we want to model our population living in this region here. But now I want to model it looking not at isolated patches, right? I don't want to model it because perhaps this is a very, very small patch and maybe the population is not able to survive because this is too small, right? Or, yeah, it doesn't have all, yeah, maybe this is too small, right? But then maybe there is some population there because it keeps receiving an influx of individuals, right? Yeah, or maybe there is some population here, but it's very small, but then it gets larger because I have an influx of individuals, or perhaps, yeah, there's something to be understood by not only studying the population dynamics inside each patch, what happens with the population living there, but also studying the flows of populations of migration between the different patches. Yeah? So how do we do this, right? So the first thing is that we have to model so I am going to number the patches, okay, number the patches. So all this is patch 1, this is patch 2, this is patch 3, this is patch 4, this is patch 5, this is patch 6, and now I want to, what would be the full treatment of this, right? I would think, okay, I'm going to look at the density of the population across this whole region, okay? I will have that in the patches I will have a high density, or relatively high density, and in the non-habitat I will have a very low density of individuals, right? But this is complicated, so I take the simpler approach that instead of thinking of the density across the whole region, I'm going to treat the whole population in each patch as we did before, as the population of the patch 1, yeah? And this is a population, okay? So I'll have in here, for instance, I'll have a system with 6 equations, one for the population in the patch 1, another for the population in the patch 2, population in the patch 3, and so on, right? What is the difference from what we have seen before? Is that now they will be unnetted through migration, yeah? So I have something like, for instance, let's assume here the simplest thing. What is the simplest thing about population growth in each patch? Let's assume that it's just logistic growth, yeah? Okay, so let me come here and write that then N1 dt is going to be R1, N1, 1 minus N1 over K1, right? And the same thing for all the other species, okay? Gn2 dt is going to be R2 N2 1 minus N2 over K2, okay? Now, if these are populations, absolute numbers of individuals or biomass and so on, right? Of course, this carrying capacity here and even the growth rate can depend on the habitat, right? So if I have a larger region, I expect to see more individuals in this larger region than in the small region, right? So the carrying capacity, as you asked, right? So the carrying capacity of a larger patch should be higher. Is it exactly proportional to the area? Perhaps yes, perhaps no, right? So maybe the patches would also be slightly different. So maybe this patch here, I don't know, is smaller, but then it's also a little bit degraded, is less productive. Maybe even the population growth is smaller here. So there would be other differences apart from area itself, okay? So the parameters of each patch would be different from each other, okay? Yeah, of course, if they are two large patches and they are exactly the same except for area, perhaps using area carrying capacity proportional to area probably works pretty well, but you know, it cannot. Yeah, so it's a did approximation. Okay, good. But well, this is not the whole thing, right? So because in the way I wrote this model here, this patch population here never goes from here to here and vice versa, okay? Yeah, so I have to include some terms that connect patch 1 with patch 2, yeah? So we have individuals going from here to here, and I will also have individuals going from here to here, yeah? Okay, how do I do that? Yeah, so, yeah, I'm out of space here, so maybe let me rewrite this down here. So, okay, so with this now I'm going to assume something very simple about this, is that each individual in this patch here has a chance of migration, and in particular of migrating from 1 to 2, okay? So if I have more individuals here in patch 1, more individuals will migrate, right? So if I double the number of individuals, I double the number of migrants from 1 to 2, right? So I'm going to write that the migration rate from 1 to 2 is proportional to the population in the patch 1, yeah? So the migration rate, the total migration rate, is proportional to the population in the source in the source patch, okay? Yeah, does that make sense? Yeah, so I'm going to add a term here that is what? I'm going to assume that some individuals will leave 1 and arrive at 2, right? So let me just check. Yeah, I write it like this. So I'm going to add a term here that is minus m21 n1, right? And the same term that appears here will appear down here with a plus sign, okay? You see? So I took out individuals from patch 1 and made them arrive at patch 2, okay? There's another assumption that I did here. Besides being linear on n, okay? There's also the fact that I assumed that there's no mortality in the middle, okay? Of course, I would also multiply this by a constant to say, okay, just a fraction of individuals that left here were able to arrive here and survive it, okay? Yeah, that would also have then to be the positive term to be a bit smaller than the other one due to survival not being 100%. Yeah? Okay, so this is one thing. But now we also have to account for the other direction. Yeah? Individuals leaving patch 2 and going back to patch 1. Okay, how do I do this? It's the same, right? So I have individuals leaving patch 1, patch 2, and arriving at patch 1. So it's the same term as down here, yeah? Okay? And now I already wrote this in a way that the contribution to the population on patch 1, right? So N12 is the population leaving patch 2 and arriving at 1. And this here is the population leaving patch 1 and arriving at 2. Okay? Good? And now, of course, with this in mind now, I can think, okay, what happens if instead of 2 patches, I have any number of patches? Yeah? So, are we ready for that? Yeah? Yes or no? Yeah? So now we are confident in our matrix powers. Yeah? Yeah, okay, nice. So, I feel like I didn't even have to erase this, right? So, yeah, I just needed to change the letter. But okay. Okay, so now, what is going to happen here, right? So, if I want to look at some patch, right? So I told patch I, right? So looking at patch I, right? So you have dni dt, okay? This will be Ri times ni 1 minus ni over ki, okay? So far, so good. And now, what is going to happen, right? So I'll have, if I have n patches, right? N patches. I have a system of n patches, right? So here n equals to 6, for instance, in this example, right? So I'll have individuals from the I patch leaving for patch 1, leaving for patch 2, leaving for patch 3, leaving for all other patches except itself, of course, yeah? Okay? So I have to subtract the migrations from this patch going to the others, okay? So I'm going to have a minus term here that is all of them are multiple of this patch, right? So if I had a migration for patch 3, I'll have a term here that is minus m31 times n1 itself, right? So all of the migrations here leaving this patch will be proportional to the population of that particular patch, right? So this is going to be minus n1 and multiplied by the sum of all the migration rates leaving patch I and arriving at some other, okay? So this is going to be a sum over j of n j I. And that's it, okay? Let me put a parenthesis here, okay? This joins from 1 to n, and with j with different than I, okay? So this is a notation here, okay? To tell that j is going to be 1, 2, 3, 4, 5, up to 6, for instance, in this example, but different from I itself. So if I'm looking at patch 1, I don't have the n11 term here, right? Because it doesn't make sense to migrate from 1 back into 1, right? If I don't want to do this, right, it would also be a little bit smart here and say, okay, I can include this term here when I goes to j. I just have to define n11 equals to 0, yeah? And then even if I sum this term is 0, yeah? So I can just say that I can erase this thing here. I can erase this thing here and just say that n y n I is always equal to 0, yeah? So no, this means no self-migration, right? Yeah? Self-migration, would be weird. Yeah, okay. Okay, so far so good. We have here accounted for all of the population leaving patch I, and now I have to introduce here the positive terms, all the population from all the other patches arriving at the patch I, okay? So what I have here, so if I have, for instance, for patch 1 here, I have n, 1, 2, and 2. For patch 3, it would be n, 1, 3, and 3, and 1, 4, and 4. So I have n, I, j, and 1, j, and j, right? So here I will have a positive term here that is n, I, j, and j, right? And j going from 1 to n again. Yeah? And then I would have once again to do this stuff here with j different than I, okay? But now that I define it nii or to 0, I'm fine, yeah? I don't have population coming from the patch itself because nii is 0, yeah? Okay, people, this is okay? This is fine or not? Yeah? Question?
But if in the end of the day we are subtracting and adding MII, it doesn't have to be 0, right?
Yeah, that's true. It would be any value and it would cancel out, yeah, yeah. But I like to put it to 0 because sometimes you want to do the stuff with the mortality, right? And if you have mortality in the migration, you're saying that the population is losing individuals due to mortality in the matrix, in the non-habitat, just by migrating from itself to itself, right? So this is, yeah. I have not included this here, but it's better to be careful, yeah? So, okay. More questions? Okay, good. So, and now what do we want to do, right? So this already is enough to do a for loop, right? So if I have the equation for any population I can go one by one, right? But of course, this is not what we want here, right? So we want to write this down as a matrix product, okay? As a matrix expression. So I'm going to write this as a vector, okay? A vector of populations g and dt, right? And then this part here is pretty much what we have seen before, right? So this will be a vector of errors, and this is going to be a vector of case, and this is going to be what? What is this here? This is, yeah, before I do this way, right? So let's look at this first. So this here, this part here, right? What is this? This is exactly, I already erased what I had before here. Yeah, it was in the other board, yeah. So this is exactly, if I define a matrix M, right? This is exactly M times the vector N, okay? So if I have, for instance, the 2 by 2 A's, right? So if I have M11, M12, M21, M22, can I do just the 2 by 2? Just because I'm already tired, right? Yeah. Okay. Yeah. You got the idea, right? But then let's just do this just to check, okay? Just to check. So M1, M2 here. What appears in the product, okay? M11, M1, plus M2, M2. And here, down here, M21, M21, N1 plus M22, N2, okay? So is this what we want? M11, N1, M12, and this is 0, of course, right? So this is 0, and this is also 0, right? So we have M12, N2, M12, N2, M21, N1, right? I do this just to be sure that I'm not inverting the indices, right? But then with some practice, you notice that whenever you have a matrix multiplication in this order, the repeating index of the matrix is the second one, right? Because you go over the columns of the matrix, yeah? Okay, good. So this is a good thing to remember, right? Okay, and this one here, this is not a product by n, okay? I only have actually here, if I look at this matrix, what I'm doing here is that for population I, I'm looking at column I, okay? At the column I, so for instance, for the species 2 here, I'm looking at the second column of the matrix, okay? I'm summing over the whole column, right? So I take all of the lines along this column and summing over the lines, okay? Yeah? Okay. Can I represent this in a matrix form? Yeah, I can. I did this in the notebook, but in computational terms, you can just use sum, right? We did this last time, right? Remember when we had the total populations yesterday, that you just sum along the columns, or yeah? Sum all the lines along the columns, yeah? So I can do this pretty easily computationally. When you do this mathematically in terms of products of matrix, this is the same as taking a vector of ones, right? And multiplying in the left by n, okay? By n. So I actually have to take this, transpose it here, yes, all right? So because now I want to sum along the column, so I have to multiply in the left, okay? Or maybe I have to transpose and then multiply, right? So yes or no? Maybe this is a bit confusing, but I don't want to go into detail because I use this mathematical notation, but I don't really care so much about it because essentially I'm using this as a tool to be able to write programs that are pretty compact, okay? Yeah, if I know how to do the sum over the columns, in the computer, this is going to work out, okay? Yeah? So my equations will be like this, right? So d and dt is going to be the vector of errors, the product element by element with n, then the product element by element of 1, and here I'm using this notation here, minus n1 over k, over the array of k's, right? I don't know any notation for for division element by element, or only for products, so I wrote something funny in the notebook that is like this, right? So yeah, of course you don't have to do 1 over k multiplied by the vector n, right? You just do n divided by k, right? So yeah, and this is a vector where each element is 1 over ki, okay? And then there's the interesting part now, okay? So this is minus the vector n multiplied element by element, because this sum over here will be a different value for each line, okay? And then I just do multiplication element by element with n, okay? So this is multiplied by the sum over the columns that I told you that this is just 1 times n. And finally, I have this term here that is plus m times n. Okay, so this is my set of equations, okay? Questions, people? This is slightly bit more complicated, but not so much. Yeah? Okay, so let's try to implement this in the computer, okay? So let's go. Yeah, I'll keep this the light zone for now. I can still be still able to read. Yeah. Okay. So I use x here instead of n, right? So other than that, I think I use exactly the same equations. Yeah. And here I was little bit more patient to writing out all this stuff here, and I arrive at the equations that I have there, right? And now the numeric implementation, okay? So once again, we have many parameters. So if I have a system, for instance, 6 patches, okay? 6 patches like this. I have 6 values of the growth rate, 6 values of the carrying capacity, and all of the migration rates, right? So we have a 6 by 6 matrix that are 46 migration rates, except for the diagonal that is 0, right? So I have 40 more parameters, okay? So it's a lot of parameters, but I represent them with only 3 arrays, right? Only R, K, and M, okay? Okay, good. And now I have this, right? So I import this stuff as usual. I want to write this model as a function of x, t, r, k, and m, right? Now I here, I define the pieces here, right? So once again, I'll put here, let me put just 6, right? So just 6 patches, okay? I define it R as all of them are equal to 1. I put the carrying capacity here at all of them equal to 10, okay? So this is a vector of 6 ones multiplied by 10 is all of them equal to 10. And then I said that all of the migration rates will be equal to 0.05, okay? 0.05. So it's relatively small migration, okay? And then I just use fill diagonal again to say that the main diagonal, the migration from itself to itself is going to be 0, okay? I added some random values here, and then I want to solve this, but this is, I call this an exercise, okay? Because I wanted you to try to do this, yeah? Okay, so this is end of class. We don't have much time, but I will go back to this example tomorrow, okay? So you have a little bit of time. Let's try to do this a little bit now, yeah? Do you have well, is my Q&A just after that, right? So maybe we can go a bit like some 15 minutes of work later, yeah? Okay, good. So, and I left a further example here in this notebook, but this is actually a challenge, okay? So this is, so let me talk very briefly about this. This is the MacArthur consumer resource model, where you have a set of resources and a set of consumers, right? And now the consumers grow as a consumer, like they only grow when they consume the resources, okay? And then of course, and generalize this with n resources and m consumers, okay? And then you have a large system of equations, and then you have this matrix that has the consumption rates, right? But now it's a little bit different than before, because now this is no longer a square matrix, right? I can have a different number of resources, a different number of consumers. I have to divide my X array into, the first part are the equations for the resources, the second part are the equations for the consumers. So this is quite a bit more complicated to write in terms of the R and C vectors, okay? So that's why I'm not proposing this as an exercise, I'm proposing that more as a challenge, okay? Yeah? Okay, but for now I want you to work on the patch model, because I'm going to use this also for tomorrow's class, okay? So yeah, time to work. Questions before we, questions? Are you more or less able to see how to do this, or not so much? Do you need some tips? Yeah. The patch model, I mean, right?
Yeah.
Not the challenge.
Yeah. Maybe some tips regarding the sum.
Yeah, the sum. Remember last class, we had this part here where we, when we were calculating the total population. Oh, I don't have the the OP here. Oh, that's bad. Okay, so you have a function inside NumPy. So let me do something an example here. So NP arrange from 0 to 16, and I want to reshape this as a 4x4 matrix, okay? Oh, I need another one here. Yeah, so I have this thing here. Let me print it, okay? So this is the matrix A, right? And I can sum it along the lines or along the columns, okay? Depending on which argument I pass to sum, okay? So let me have both here, okay? So you see the difference. You see? So here I sum the columns with x is equal to 0, right? So I'm summing the lines, okay? And I have the sum over each column. Oh, sorry. No. Let me print a little bit more carefully, right? So yeah. Sum along x is 0. Yeah. Yeah, you see. So you see, here I sum 4, 8, 12 to get 24, 1, 5, 9, 13 to get 28, and so on, okay? So I sum along the 0 axis, that is, I sum at the lines, okay, to get a total sum by column, right? And when I put x is equal to 1, I sum it along the column, so I have a total for each line, okay? So this is the difference of these two cases, right? So here we want to sum the sum for each column, right? So I think you are going to use the first one, right? Yeah? Okay. Good? More questions? Okay.